Okay. And the crowd quiets, the tension builds. Good evening, everyone. Welcome to the May 1st meeting for the Tucson Amateur Astronomy Association. This is our regular first Friday of the month general meeting. We are here in the Stewart Observatory Auditorium with members here in the room, but we also have members online on Zoom, and we have the public joining us for a good part of our program tonight, streaming live. So welcome, everyone. We've got, as usual, quite a number of things on the agenda. And we are going to try and start tonight with a message from our former president, David Levy. I know everyone anticipates this at the beginning of the meeting. David, are you with us tonight?
Can you hear me? Yes.
Yes, we can hear you, David. Welcome. David, can you start us off with a poem?
Okay, I hope you can all hear me. I am so glad to be here. I had written to Ed that I wouldn't be able to be here because I would be in Kalamazoo for their 90th anniversary, but I couldn't make that. I wanted all my friends to know that I have been having some pretty serious medical issues. The main one being anemia. When I got into the hospital a week ago Thursday, my blood oxygen was down to 5, and they said if it had gone down about 1 more point, it would not have been survivable. So it was close, but I'm here and I'm feeling a lot better, and I'm so glad to be with all my friends tonight. My quotation tonight is going to be from one of my very favorite poets, Walt Whitman, and I'd like to introduce the meeting with that. It's called A Clear Midnight. This is thy hour, O soul, thy free flight into the wordless. away from books, away from art. The day erased, the lesson done, the fully forth emerging, silent, gazing, pondering the message, and finally, night, sleep, death, and the stars. Thank you so much, Ed. I'm back to you.
Thank you, David. Take care of yourself.
I will do my best. And thanks to David Rossiter for helping. And Tim Hunter.
Tonight, we have got a guest speaker who's coming to us from Phoenix. He belongs to two of the clubs in Phoenix. We let him come anyway. Now, Tom is a very well-respected amateur astronomy. Tom Polakis has been in astronomy for, let me just say, many, many years. And he's an observer, he's an imager, and he is a published author on subjects in astronomy. One of the subjects he's going to talk to us about tonight is are the small objects in our solar system, asteroids. Tom Polakis, please, Tom, come up and share your thoughts with us.
All right, so hold your applause. I haven't started speaking yet. So, okay. I am getting feedback, which I think is from here, and make it go away before. How about now? There we go. It was coming out of my laptop speaker. So we're off to a good start. Okay, so here's first thing I'm going to do is share screen, and then we'll be on with it. Share screen. Oh, presentation, right? Yes. So, ready to roll here? Okay. How's that looking? Okay. So, this talk is, I thought of all sorts of possible clever titles, and I came up with all about asteroids. So we got that going. Let me find the page down. And most of the people here are old enough to recognize what this is. So the main premise of this talk is going to have to do with how tiny the angular size of an asteroid is. It's really small. We call them minor planets. And that's just a different name, an alternative name for asteroids. And I'm not going to get into what's a dwarf planet or nomenclature that way. But what I am going to get into is what's the size of a large asteroid like Ceres, and what's that correspond to an angle in the sky. And the largest one is not even 1 arc second across. So if you want to know what an arc second is, here's my image of Jupiter, and there's Europa, and that's 1 arc second. So if you have perfect seeing and you lucky imaging, you might capture a very large detail on Ganymede or even Europa. But that's what we're challenged with, and we want to learn about asteroids by as many ways possible without having to go out to them with a craft. So what I'm going to cover, and I'm not going to read it, are these topics. And when I get to the end of the talk, 45, 50 minutes from now, we will have gone through all of these. So we start with discoveries. And even before the first asteroid, way before the first asteroid was found, Kepler kind of knew there was something out there. And he said that there has to be a planet. There's got to be something, because we know about how far away Mars is and all these inner planets. And then we know Jupiter's way out there, 5 astronomical units out. And there must be something in that wasted space. And so another way of looking at that, they call this Bode's law or Bode-Titus law, that you have this exponent in the equation at the upper left, and that describes, not by any physical rule, but it's a nice mathematical oddity more than anything, where each of the planets are and where's number 4. So number 4 has to be where those asteroids are. And this was known before, again, before 1801, before the first asteroid was discovered. And so you had a group called the Celestial Police, before you get distracted by Piazzi's picture there. And what they did was took 24 zones of 15 degrees of right ascension each, up in the northern hemisphere, of course, and divided the sky up that way and began searching for asteroids. We didn't have photography or astrometry or any of that kind of stuff back then, but you just had visual means of doing that and charting things and trying to find something besides a comet that's moving out at that distance. Piazzi was not even a member yet, but on 1801, January 1st, so they had a Y1.8K problem back then. So he discovered with a 75 millimeter scope, he's just star cataloging, he's not really looking for asteroids, and he found the first asteroid, and it was named Ceres, and we're all pretty familiar. It's one Ceres, and then in the next 6 years, up through 1807, there were 3 more discovered. Then there's this big long gap, and I'm going to show you plots now that'll show you this gap before the next asteroid was discovered. So you have the big 4 that are all reaching 7th magnitude or so, and then this plot shows those 4 over at the lower left corner, going up through 1807, then this big gap where nothing was found despite people searching for asteroids during all that time. And then finally we have number 5 shows up in 1846. So the reason for that is that all of this to the right on the curve is faint for the day, magnitude 9 or fainter, whereas these are almost naked eye objects or really small aperture telescope objects. So you can see that this plot starts to climb, and by the excuse me, by the end of the 19th century, you had your first photographic discovery, and prolific discoverer Max Wolf found 248 of them, which had to be nothing like finding asteroids today. Finding these asteroids was an incredible accomplishment, and he's one of the greats in asteroids. So 322 discovered visually, and I just give a summary as when the photographic discoveries began. And there's just the first 8 years, that's what he had found in that time. So when I've been doing my asteroid work, which I'll get to later, so many of them begin with the biographical information that they were discovered by Max Wolf and other people at this same Heidelberg site. So let's expand the scale, or actually begin at the year 1900, where we already have about 400 asteroids, and we'll see this curve growing, but slowly up to 1960, and it's at about 2000. And when I'm putting this plot together, I thought something's certainly wrong because that step change could not have happened, but it did happen because at Palomar Observatory, and I have the shirt, the Palomar-Leiden asteroid survey just in less than 2 weeks doubled the count of asteroids. And so there are similar changes like that where a survey was dedicated to just finding asteroids, photographic surveys, and before CCDs were in service yet, and these big jumps in asteroids. Now we'll take that scale and begin at 1980, when you already have a substantial number of asteroids, and when CCD cameras started becoming routinely used in professional astronomy in the mid to late 90s is when you see this start to really take off. And so this takes us almost to the present. This is a little bit old, this slide already. It actually is at about 1.5 million known asteroids now. And now that the Vera Rubin telescope is operational, that'll just become many millions more in no time at all, because it's going to be going so faint and with such a wide field of view. And here's the plot going all the way back to the first asteroid discovery. And if you like reading plots as much as I do, you'll just see how flat it is and then what has happened recently in recent years. And many of these are 21st, 22nd magnitude, and they are house size, or I don't know how many bananas that is, but not very big asteroids. What's happening now to find asteroids, and amateurs are using this to discover asteroids. I won't get too far into the explanation, but they call it synthetic tracking. It was invented by this young genius named David Parrott in Arkansas, who has a piece of software called Tycho Tracker. And this is getting done right here at the Catalina Sky Survey up on Mount Lemmon and in other observatories in the area by professionals to discover asteroids. Originally, what you had to do was look at a set of plates and have software find an object that's moving, but you don't know the vector, what direction and how fast it's moving. So Tycho Tracker would do synthetic tracking. You need a good graphics card and a powerful computer, and it would look at every possible vector so that you would end up with something that looked like that at the end of it. So Daniel, who invented this whole technique, tried it with his 5-inch telescope and just tried it. These are not discoveries at the bottom of the slide, and found almost 300 asteroids on his first night. So a 3x3 degree field of view, and he does that right away. So obviously very promising, and it's used today to discover asteroids. Here's a pie chart to show the main discovery locations and discovery sites. Spacewatch is at Kitt Peak, a 0.9 and a 1.8 meter telescope. Mount Lemmon, also the Catalina Sky Survey are right here near Tucson, of course. Lonios is obsolete, but went in the late 90s, early 2000s over on Anderson Mesa for Lowell Observatory. So just a pie chart of that. And then I thought, at least while I'm showing pie charts, that you want to see this classic illustration here. So, all right. So let's look at orbits. Next little subject we can look at, and I'm not going to get deep into orbits, but there's a lot to them. Back in the day, not that long ago, actually, well, I was alive, there was just the asteroid belt. It's that area between Mars and Jupiter, as I showed you earlier. And now that's an extreme simplification. We just call that the main belt. And then we have inner, middle, and outer main belt. But then you have all these, the Apollos and the Atens, the Earth-crossing asteroids. You have all sorts of crazy different orbits that they are in, and we categorize them that way. There's Trojans. This Greek stone is typically also called Trojans, that are flanking Jupiter in its orbit on 60 degrees on either side of it. And then there are orbits that are much larger, that go way out past Pluto, and they're trans-Neptunian objects. And I want to show you what's called a near-Earth object, and that's anything that gets within 1.3 astronomical units of the sun. So it may not really get near the Earth, but they had to come up with a definition for it. And so here's just an example of a near-Earth object, and I'll get into that a little bit later as well. So for these orbits, how do you define that? So the first thing you need to do is called astrometry, which is getting precise positions. And you can't do this by just having one or two positions. You really have to have it so you can start to define the arc of the asteroid. So you'd like to have that at multiple epochs, at least a few days, even a week or a month or something, to start to really get a precise orbit where you can compare your theoretical orbit, the curve it should be following, to what the asteroid's really doing. And something that still happens today is there's discoveries and they just get lost for good. The very first asteroid, Ceres, was lost for a year before it was recovered and then categorized and then shown, not characterized. So after you get those positions, you come up with what's called orbital elements. And the easiest three to understand are highlighted here, and then period as well, which isn't really an element, just for information. And I'll show you those right now. So one of them is just called the inclination. You take the Earth's orbit around the sun, it defines a plane, we call that the ecliptic, and what's the angle that is onto the ecliptic. Next, this has got a giant orbit here, is just called the semi-major axis. All of these orbits are elliptical. Take the long axis of the ellipse, and what's half of that? What's the radius of that ellipse along the major axis? And then there's also the eccentricity. Eccentricity is how far it deviates from a circle. Circle has an eccentricity of 0, perfect circle. Ellipse, as that number gets larger and larger, is just a longer and longer ellipse. And a parabola, which many comets are on, that's E equals 1. That's an eccentricity of 1. But almost all of these are going to be between 0 and 1. So all three of those are pretty easy to understand. But there is such a thing as an eccentricity that's greater than 1, and that was only first discovered, I think it's 4 years ago now. And now there are 3 of them that are known to have an eccentricity greater than 1. And what that means is it's a hyperbola. That means that it's not in any way bound to the sun, and it's racing through our solar system from some other sun. And that in itself is cool. I mean, that's just so exotic that finally that's been found. And now there are 3 of them that are known to have come from other stars, which are almost impossible to determine what other star. They can give a region, but now for once, we have asteroids that may be older than 4.5 million years old than the solar system. One is thought to be 7 billion years old. So that is a cool thing to know. So what does that mean to this guy, Avi Loeb? Money. So Avi Loeb, I have to tell you about. He was the director of the astrophysics department at Harvard, not some schmuck. He's really and very well published, but in the late stages of his life, decided that these hyperbolic orbits must somehow be extraterrestrials. In one case, it has to be propelled because they saw non-hyperbolic motion, can't think of the word. So that must be aliens. That's his explanation for one of them. And then the most recent one happened to pass kind of close to Mars and Jupiter. So it must be on some sort of reconnaissance mission. Also the explanation, aliens. So, and that's Avi Loeb's late career way of making a lot of money, bypassing a scientific method and going directly to a popular press. So there you go. Astrometry, which I mentioned earlier, is just a way to get real good positions, real good, and I mean really way, way smaller than hundredths of an arc second, thousandths of an arc second type of precision of these positions. And what happens there is they call it a plate solve, a plate solution. So you know the locations of hundreds of stars on your CCD image or CMOS image, and it knows where they are and where they are in your image. And now this interloper, this asteroid, or whatever your object is, you can compare that and do some sophisticated math and get great positions. And so that's what's all required to get these orbits that we have. Now what decides how bright they are? Where it doesn't get used often, extrinsic. What's the distance of that asteroid from the Earth and from the sun? And then the phase angle. So when this thing is, if any of these come exactly to opposition, even close to exactly to opposition, they'll be following this curve of brightness and then they'll spike, which is just like if you're up on a mountain and you look into a forest and the sun's directly behind you, you'll see what's called a Heiligenschein, and you'll see it on pictures from Apollo of the moon exactly opposite the sun, that there's a flare like that. So that phase angle is important. And then what's also important is obviously how big it is, and then its reflectivity. So here's Vesta and Pallas at about the same size, but their albedos are so different, their reflectivity are so different that they're going to have quite a bit of different brightness. So there's one takeaway in this talk, which I only learned in the last couple weeks. This is my 6th time doing this talk, that I only learned this a couple weeks ago. That's another definition of albedo. And this is as non-astronomical as anything in this talk. That part of an orange is called the albedo. There. Now you know. All right, so what I did then was I tried to generalize this and assume some albedo, and don't worry about the phase slope parameter G, which is given there. I just put a couple assumptions, and then I said, if I know about the size of an asteroid, can I figure out what's the opposition magnitude? If I know the size and the distance from us. And that gray is idealized asteroid belt out between Mars and Jupiter, which is where most of these asteroids are. So then I just figured I'll just pick 2 asteroids arbitrarily and just see how they line up. And yeah, there's my selections. No applause, please. And so here's some more. And it actually worked pretty well. It was just something, a little spreadsheet. I'm a spreadsheet nerd. So it was a spreadsheet exercise that I did. And here's all these asteroids where Ceres will not quite reach 5th magnitude, but reach 6th magnitude or so. And you can plot all these and kind of figure out, all right, that's about how bright they are. And if we go back to this one, I've been able to visually observe the asteroid that was named after me by Brian Skiff, and it reached about 15th magnitude at a favorable opposition. Jennifer's reaches 20th magnitude, and it is an object that can be captured in images. So this plot then, since we're talking about brightness of asteroids, just shows 3 oppositions of an asteroid and how wildly different their brightness is when they come to opposition, which has an easy solution. Those are all oppositions. And we'd see this with Mars. When Mars is at a close opposition, it's as bright or a little bit brighter than Jupiter and huge, 25 arc seconds. And then when it's an unfavorable opposition, it gets up to -1 or so, not nearly as bright. And so this affects what I'm going to observe, which I'm going to get into a little bit, what I'm interested in, because I'm pretty limited at my site in the urban jungle up the freeway from us. There are several types of meteorites, and I'll spend just this slide on this, not my area of expertise by any means. And these also reflect what we see as meteorites when they hit the ground, which are little chunks, tiny meteorites. Okay, so move into, now we've discovered the asteroid and characterized its orbit, we're allowed to give it a name. But before we give it a name, you submit this. And this just one example is found at Kitt Peak at the 0.9 meter space watch, the smaller one, the earlier one. And they got a first image I'm showing on the bottom here, showing 3 superimposed images of the same star field with the asteroid moving across it. And so that originally gets a designation that's the year and 2 letters representing the month, the half month, and the number and sequence that it has. As always, we run out of letters and numbers as the population of these explode, but this is still a good system for what it is. Then, after you have computed an orbit, now the discoverer of the asteroid is allowed to propose a name. In this case, the name that they proposed way back after it was characterized, they knew it was a binary asteroid, found that with radar imaging and with light curves. I'm going to get into that also. And Didymus means twin. And this is a very significant asteroid as far as what has happened in the past couple of years involving it. So I'll just run through a few asteroid names. Great, United States people. And then we move into artists, Picasso right down to Frank Zappa, Pink Floyd's in there. And all 4 of the Beatles have been named individually. They have asteroid names. Here's some local people, local to Phoenix anyway. Gene Lucas, Randy Peterson, Ron Greeley. And then finally, they were able to get away with all even and all odd. Pretty cool, eh? What I'm the most interested in, and what I have done a lot of, all sorts of work with photometry, was just measuring brightness and color. So I'll show that here. And I like doing asteroids a lot because I don't have to mess with filters. And what we're doing with asteroids then is you will take a series of images through the night, maybe 50 to 100 images of an asteroid, and do that on successive nights or on as many nights as you can. And you'll end up with what's called a light curve. And so that's this curve of all these points that you see here. And you can see that right now, they look like they might have a cycle. And what's happening is we're seeing the brightness of the asteroid vary. Let's say it's an oval, a football shape, an ellipsoid. So when its small axis is pointing toward us, it's fainter. and then gets brighter when we see the large view of it as it rotates. And you also are seeing within that there are variations due to craters and mountains as well, and that gets to more finesse. But if we just take this simple light curve that I took over the course of 7 consecutive clear nights, you can do what's called a Fourier transform, and you don't have to know any math because the software does all of this, and it'll take that raw light curve and change it into what's called a phase light curve. So from all this mess of points, we were able to determine that it has a rotation period that's a little shy of 30 hours. And the real large amplitude that we see has to do with it being very elongated. If it was perfectly spherical with no features, then you get a light curve that's flat and you can't determine anything with it. So that's called a Fourier transform. And then this here is called a Courier transform. There you go. Yeah. There's a really cool site that does this, just what I was describing. So if you're looking pole on or the asteroid is spherical, you just won't get much amplitude to that light curve because you can see the brightness isn't going to vary enough for you to determine anything. Or you can have something that's real irregular shaped and elongated, and you'll get a large amplitude. You do this at 3 or 4 points around the solar system. Obviously, this takes years and years. And you take it at different locations in the solar system, and you can create a shape model. And that's what we see in the lower left is a model based on multiple light curves, not just knowing the rotation period, but doing it 2 years later, and do it several times. Now you have enough information in it to start to even see topography or shape of your asteroid, which is great. So the shape model database is the tortured acronym called DAMIT, which is a database of asteroid models from inversion techniques. So I think a name for everything. So here's a couple of my light curves that illustrate what I was talking about. This is kind of a not great solution of 54.7 hours, but it actually corresponded with people with larger scopes at darker sites. And that's almost a gray cue ball, like you see there. Or you have these where the amplitude is over 1 magnitude, and that has to be this very elongated thing with topography, again, with craters that are changing the illumination even as it's barely rotated. So one of my 15 minutes of fame was that at one point I owned the slowest rotating asteroid record. So this one, we had a remarkable stretch of clear nights in late 2021 and early 2022. And once I saw how slow this was rotating, like it was barely changing from night to night, then I knew I didn't have to take 100 data points or 100 images. I could take just 3 or 6, and that would be good for that day. And so I just kept doing that night after night until we ended up with an asteroid with a rotation period of 75 days. Which was pretty cool because the record before that was about 60. And then, of course, 3 months later, it might have been less than that, a paper came out in the Astrophysical Journal in which they had found 30 of them that were 100 days or longer. So there went my 15 minutes, but it was great while it lasted. And so it's kind of a discovery. And I just like sticking with these if we have enough clear nights. And boy, that has not been the case in the last 6 months or so. But it was great having all these photometric nights or even partly cloudy nights where it was clear enough to get these images. So I didn't mention, I'm not really big on mentioning the equipment. My equipment is a 12.5-inch imaging Dahl Kirkham. The field of view is about 3/4 of a degree by 1/2 a degree. It's on a 10-micron mount, which is the best mount I could have ever possibly chosen, just unbelievably reliable. And I shoot from Tempe, Arizona, where there is no sign of the Cygnus Milky Way overhead, and the sky brightness is 4.5 magnitudes brighter than the natural level. So the SQM reading is 17.5 consistently there. And yet you can still do stuff like this. As long as it doesn't get down below about 16th magnitude, you can still do this type of work. And it's in a roll-off observatory in the backyard, so I can just open that and use it every night. And that's how this stuff gets done. Another discovery, and there are now 600 of these, but I discovered I was part of the discovery of one binary before this, and this is my independent discovery of 1803 Zwicky being a binary. And sometimes you get all these data points, your photometry, and you want to throw points out because it can't be right. It just went crazy. And I almost threw these points out in the upper left figure, and then noticed that it was happening again and again on different days as I did this light curve. Like I had a rotation light curve, but here's these dips. And so what was happening was those are called mutual events. So not only are you seeing the rotation, but every time there's a transit, now you don't see the combined light of the two, you just see the one's brightness. And there's a occultation, which is 4, and you'll have that characteristic like these V-shaped drops in the brightness. And before then, nobody knew that this was a binary asteroid. And I was really happy that the name was 1803 Zwicky because he's one of the great characters of astronomy. Fritz Zwicky, he once said of a fellow astronomer that he's a spherical bastard because he's a bastard no matter what angle you look at him from. Yeah, so it was good. And eventually you get enough of this and you get a rotation period that's pretty precise, 2.7 hours, and you get an orbital period. So you get both of those fall out of some pretty sophisticated Fourier analysis. And then claim to fame is that you get an essential bureau telegram. Bob Stevens helped out with one night. He's in Southern California. And then also on the top line, I have to mention Petr Pravic in the Czech Republic is the man when it comes to asteroid rotation, binaries, all that stuff. There's probably nobody better in the world at that subject. And so I ran it by him before I went any further. And once he congratulates you, then you know it's real. Kind of cool. So here's a scale model. Better if you know LA, but it's like going from Ontario Airport almost to LAX kind of thing. That's the separation in size to scale of the asteroid and its companion. So I've talked about photometry as a way of taking these point sources and making sense out of them. Another way, which I obviously can't do in my backyard in Tempe, is radar imaging. So radar images are similar to ultrasound. This is my grandson Lincoln when he was -6 months old or whatever, and now 12 years old. And it's kind of like that you take a large radio telescope and send a signal at the asteroid, which hopefully is pretty nearby at the time, nearby being within 10 or 15 million miles from us. And so then you compare the return and a transmitted signal. There's got to be a time delay depending on where you're pointing on that asteroid, and then a Doppler frequency shift. And polarization is kind of beyond the scope here. So normally you have to rely on the sun's illumination. In this case, you can actually control the illumination because the radio telescope is doing the illuminating. This was done routinely with 2 imaging facilities, and the one on the top, I think everybody knows the fate that big receiver on the top crashed down on the dish, and that was the end of Arecibo Observatory. But Goldstone in Southern California is still operating, and there's some movement to get Green Bank and others involved. So all of this is done. The radar imaging is all coordinated by a group at the Jet Propulsion Laboratory in Pasadena. First time that we had a radar detection of asteroid was 1968. The first shape model was in 1977. Eros is a very interesting specimen. And then here's a resolved radar image with the thing on the right looking like something from dental x-rays or something. But you'll see a lot of that with asteroids that if they're not binary, quite a few of them are dumbbell shaped. And they're rubble piles and they're just fused together. So now I have some pretty cool animations that I have nothing to do with creating, but this is what you get from the radar imaging. So here's Tutatus, Didymos, and Dimorphos I mentioned once already, and I'll mention a lot more here in a few slides. And a couple more. Here's one at 3 lunar distances and some rotating. So all of this is just kind of magic to me. You can take photometry, discover these. If they're close enough, you can do this kind of thing. And it's another way to find directly what's the shape of an asteroid. A third way is occultations. The leading occultation guy in the country for the International Occultation Timing Association has recently, about 5 years ago or so, moved to Fountain Hills, which is suburban Phoenix. That's David Dunham. And we have some other very good asteroid occultation observers. An occultation is just this. It is one body passing in front of another. So what I thought I'd start with was a terrestrial example of an occultation. So they're going to demolish the Georgia Dome where the Atlanta Falcons played, and that was going to be a spectacular event. And this photographer got set up in exactly the right place to photograph it. And then that happened. And then the best part is when the bus drives away after it's over. There you go. So I decided not to include the sound on this of whatever the photographer was saying at the time. So that's what you do with an asteroid occultation then, is you set up, it has a path. It's going to go in front of a star. So you set up a bunch of stations perpendicular to that path, and you'll watch the star disappear behind this asteroid. Neither the star or the asteroid have any angular size of substance that you could ever resolve, but by knowing the times that it disappeared, you can infer the shape of the asteroid and the diameter and other stuff. So there's a way to do this. There's software. I'm not going to spend any time on this slide. And the thing, you can even do this with the Dobsonian by what's called pre-pointing, pointing the telescope where the action's going to happen in a half an hour. Of course, aperture is better, as in every aspect of astronomy. And you can even use planetary video cameras. So the equipment is not that sophisticated, but you do need good timing down to milliseconds. So you want to have that really under control. And this is being done by amateurs with telescopes that are small as C-star 30s. So you can bring anything out and get data, and that's pretty cool. So we'll look at a few results. Here's a known binary asteroid. The person at station 4 in orange saw both disappearances by the primary, and they look about like that. So you figure out that kind of thing. And here's a good one where you knew the shape from a shape model, you knew what to expect. You got all these chords in the asteroid occultation and the shape model overlaid on it beautifully. So it's a good example of two different methods corroborating. And here's a spherical shape where you wouldn't be able to use photometry very well to determine anything. But if you had real precise photometry, you could do a shape model of it. And this one had a lot of chords going through it and some recognizable names down there. My buddy, J.F. Goot from France, he lived in Tempe where I went to ASU for a couple years. Now he's a professor at Mississippi State. He had this happen, so watch the arrow, disappearance, disappearance, let it run one more time. So he watched this thing disappear, disappear. Nothing was known about the shape or anything about this asteroid. Even light curves didn't exist when he did this. And by an occultation method, just going out in his backyard with the scope and watching this happen, he was able to show that it's definitely a binary asteroid. Later on, somebody did photometry, the type that I like to do, and showed, yeah, there's mutual events, and confirmed what JF found, which is quite the discovery and very esoteric, but it worked. And here's his Central Bureau card, telegram, as they call them, on his discovery from Starkville, Mississippi. So I'm going to show you the discovery method. So right now, how are binary asteroids discovered? The vast majority of the now 600 or so are done with photometry, with light curves showing these V-shaped mutual events. Then there's direct imaging, radar imaging done by pros, and even adaptive optics. And I crossed it out on purpose. The last time I gave this talk, there were 8 discoveries total ever by stellar occultation, and then one of them was JF's. Since then, JF has found another one by the same method, by watching a star disappear twice from his one site. So that's kind of what we got on binaries. what I like, and the reason I'm putting these three arrows here, are when things, totally disparate methods in astronomy or any science, all correlate with each other. And so here's an adaptive optics image. That separation is ridiculously close, 0.12 arc seconds, but it's showing the binary and its secondary and the primary. They're about the same size. Here's an occultation result from 2011 that showed them very much as binary. And then here's my photometry, which shows the arc that you see, kind of this small amplitude arc, is rotation, and these two V-shaped things are mutual events. And when they're the same size, the mutual events have a huge amplitude, as much as 3/4 of a magnitude. And that's what we're seeing here. What they call this is synchronous rotation, which is what the moon does around the Earth, where it just presents the same phase. So the rotation period is the same as the orbital period. And here you have these three different methods that work. And so if you're into the nerding out with this type of science, this will just really make you all happy. Here's a curve of known binary asteroids. We didn't know any before 1994, and now we know over 600 of them. What we don't see in this curve is it going vertical or concave up, if you will. It's just kind of going linearly with time with all these methods. So you don't see this happening like you do with discoveries of asteroids in general. And you have spacecraft visits. So I'm not going to read this slide, but this just shows some of the highlights of spacecraft that we had go by asteroids. The first time was Galileo back in 1991, and it gave very nice images of Ida and Gaspra. We have a sample return, an impactor, which I'm just going to show a little bit of. I could do a whole talk about the DART mission. There's a great image, Gaspra and Ida. And here's the near Shoemaker, which is wonderful, 433 Eros. And here's the one more, of OSIRIS-REx, which touched down in the upper right. You'll see the video of that happening, and then sent this capsule back to Earth and landed in the Utah desert. So amazing, some of the stuff that we can do. And now my favorite one, because of my personal involvement in it, was Didymus and Dimorphos. We're seeing a binary going off in the lower left corner is the primary. And now we're going to smash a spacecraft directly into Dimorphos, its companion. This will slow down a little bit. And here comes the last frame. And there it is. By doing that, and the whole purpose of crashing a spacecraft into an asteroid's companion is we know really well to great precision what its orbital period is before we impacted it. So if we can have the asteroid going through space and we crash into it with a spacecraft of known mass and everything, how much will that slow that orbiting companion down? And when it slows it down, it's going to move to an orbit that's a little bit smaller. And when it moves to an orbit that's smaller, the former period of about 12 hours became 11.5 hours. And countless papers were written on this. I was fortunate to be involved in a program I got hired on by Lowell Observatory, mainly because nobody else wants to stay up till dawn and operate the telescope. So the 42-inch telescope at Henderson Mesa, once the object got high enough, which was midnight early on and 10 at night later on, like by December, I would point that telescope at it for the whole night. And since it's an old telescope, you have to babysit it and watch it every half hour or so. And it was at a declination of -30 degrees when this happened. So really far south. So all of the results that made it into the paper in Nature were from South Africa, South America, even Australia. And one of the authors, or one of the sets of authors, was us way up north at 35 degrees north at Lowell Observatory at the Anderson Mesa station. So that was pretty cool. We were the only site north of the equator to monitor it, and we got results that were good enough to augment the paper. So by knowing how much you slowed the asteroid down, how much energy you put into it, you could start to determine when that killer asteroid's coming toward the Earth and we want to deflect it so it doesn't hit us in Arizona. How much mass do you need and how much velocity do you need? And the answer from this is it's a whole lot more than what we put into that. So it would take multiple craft or a lot more velocity, and it's got to come in oblique to this path. But it's a start. It's the first time that's been done, and a lot of great science got done. When I was working there, I got to take pictures of the asteroid, which everybody kept accidentally calling it a comet because it had a tail of debris that came off of it due to the impact. First, it was real large particles, but even 3 months later, there was still dust flying off of that, which was really cool. And what's going to happen in November is the European Space Agency's Hera spacecraft is going to orbit Didymos, and we're going to get a real good look at the carnage from this impact from the spacecraft. So it's all been a real fun program to work on. And I mentioned mutual events, and this is sometimes what they look like, are really convoluted and take multiple nights of data to really make sense of. But that's how we could determine by doing the same thing, the Fourier analysis, that it was slowing down the orbit or speeding up the orbit, bringing it more inward by about a half an hour, 33 minutes precisely. And here's a few more spacecraft missions. At the bottom, I mentioned that we'll have Hera, which is coming up soon. It's coming up in 7 months or so. We'll have something that's going to be really interesting to look at. All right, near-Earth asteroids. I'll spend a little bit of time with that. And so I mentioned near-Earth asteroids if your perihelion's less than 1.3 AU. And now we have them, the discovery methods have got so good that we see them passing, only an Earth diameter or two away, and we can actually characterize those. So there are some that are even called potentially hazardous asteroids once they get above a certain size threshold. But we've discovered most of the really large asteroids. Anything larger than a kilometer, almost anything has already been discovered, and that's not much of a concern to have the Earth impacted by that. This real busy chart, the whole theme is so as you go from left to right, how much devastation, which is just a function of how big it is, and then how many have you discovered. And so the area that we're concerned about is the blue area where it's like city could still get wiped out by an asteroid that hasn't been discovered yet, which is only 100 meters or 50 meters. That's still enough. Meteor Crater was a very small asteroid, and we're all familiar with what it did. Yeah, let's go past this slide. It's just near-Earth asteroids by survey, and Catalina Sky Survey is really kind of taking over the game. That's what's happening here. So let's finally go on to meteorites, excuse me. And yeah, so meteorite is just what you call it when a meteor has entered and hit the ground. So a question I was asked on one of these forums is, if it's a meteor, it hits the ground, now it's a meteorite, and it bounces in the air, is it back to being called a meteor again? So who knows? What happens is we get hit by 1 meter sized meteors all the time, every couple of weeks, but those are almost always landing in the ocean or in uninhabited areas. So what we want to do is have a way to discover as many of these meteor trajectories as we can. They originate from asteroids. So if you can get enough stations to find the same fireball, you can measure it through astrometry, measure their position from these different places, and you should be able to triangulate and find out whereabout did that meteor hit. And this is a site south of Flagstaff, the Lowell Discovery Telescope. The auxiliary building has this tiny little dome on it with even tinier cameras that are about that big, and they are pointed in all sorts of different directions in the sky with the sole purpose of observing meteors. And if you find a fireball here and then 100 miles away this way, 100 miles that way, sees the same meteor, the parallax will tell you and the vectors will tell you about where it landed if it was bright enough to hit the Earth or big enough to hit the Earth. So these things are going and getting way better. I was fortunate that while I was doing the asteroid impact studies, I got a call from my hiring manager, Nick Moskovitz, said, stop everything you're doing because David Rankin, Tucson guy at the Catalina Sky Survey, found an asteroid only 3 hours before I took this image that's about 1 meter across, but we know its vector well enough that we even know about where it's going to hit the Earth. So see if you can get an image with this 42-inch telescope. And that was an exercise in patience because every minute it was moving 1/3 of a degree. So 20 arc seconds per second. And now you got to find that, but the ephemeris for it is always changing. So you had to refresh that and move the scope. And fortunately, I was able to get one image out of about 10 attempts that showed the object with the stars trailing by. So it just kind of a novelty image. Half hour after I took this, there was a meteor, and the meteorite, unfortunately, well, fortunately, landed in Lake Ontario. Was not recoverable, but real close to the predicted impact site. So there have been successful meteorites. One of the most famous is this one in Sudan, where it was tracked where you could find out when the large and then the smaller particles would hit the Earth, or small and the large ones later. And you could get that whole trace and then send your search party along that line and look for meteorites, which they found a number of in Sudan. So I mentioned Nick Moskovitz. He put a team of us together. Jennifer and I went, and a team, maybe, I don't know how many, a dozen or so people, maybe more than that. And we went out to near Gallup, New Mexico on the reservation and had a search party look for meteorites. And we did it for 1 day. The rest of the group did it for 2 days without success. It was a recent snow melt, and you can kind of see from the puddle in the foreground that this was the biggest challenge of the whole night. So the whole day. So carrying around lead boots as they go through the mud the whole time. Unfortunately, it was not a successful meteorite hunt a few years ago, but maybe you'll try it again. All right, we've gone through all the topics. We're at the end of the talk, almost, but I got one more thing I want to show you. Well, 5 or 6 more slides. And this is just stuff that I've done in the backyard that may or may not be interesting to you. Just some movies and images. Here's one that is only 4 Earth diameters, not even 4 Earth diameters away, streaking across the sky. And so the astrometry and the orbit calculation has gotten so good that this can be done a day or two before, and then you have your ephemeris and you just point the telescope there. I mentioned J.F. Goot, my buddy in Mississippi. We both observed the same asteroid. He had clouds, that's why his is not a continuous dotted line. So he aligned the 2 frames, did astrometry and did a plate solve and got them aligned, and he could show by the parallax between our 2 paths, and we're almost at identical latitudes. We know our distance, and it's about 3 lunar distances away. So, and he got the answer within a couple % of its distance. Sometimes you have nice fields of galaxies, deep sky objects. If you haven't seen by now, all of my work is monochrome, done a lot of times through clear filter or photometric filters. So here's a deep sky field with some galaxies in it. Sometimes they not only hit cities or buildings. This one was in textbooks back when I was getting started in the 70s. This woman actually got hit by a piece of this asteroid, which I imaged only a couple years ago, and see that she has a big scar, and she was a sizable target to get hit. So here's the source of the Geminid meteors. 3200 Phaethon is a dead comet. It's just an asteroid now, but once in a while, it's in an eccentric orbit. Once in a while, it makes a pretty close path. And here it is going across some star fields. So I like stuff like this in astronomy more than pretty color pictures, things that have kind of a story behind them, if you haven't noticed that by now. Another one going across the sky. This one, you can actually, without doing photometry, without measuring precise brightness, you can watch it rotate. You can watch it fade and brighten just as it goes across there. So even though it's a point source, you know, it's doing something and had a real short rotation period. So I like this cluster. It's in Monoceros NGC 2244. I found out that a pretty bright, low-numbered asteroid is going to pass through it. And that was pretty cool. But if you look closely by the labels, there are a couple of 16th magnitude asteroids in the same frame. And that's the kind of stuff that you'll find, is that if you go deep enough, there are always asteroids in your frame if you're along the ecliptic or near it. So vanity project, here's my own asteroid 4078, just 4 hours of imaging. It has a real short rotation period of about a little over 4 hours. And now really getting faint, my buddy Mike Wiles is now at the Chiricahua Astronomy Complex, which everybody here should be familiar with. And if you look at the top of these bars, so there, I can't see the fourth one at all. He's recorded Jennifer's asteroid when it was about 21st magnitude. And I can only get I can do photometry to almost 16, and I can get to about 18.5 from my backyard observatory. But this is what you get with the same aperture at a dark site. And Mike does this remotely. I thought this was great that he followed up on his request. So that's my speech. I hope you got something out of it, especially the bit about the albedo of an orange. Don't forget that. And now it's time for questions that I may be able to answer. Oh, yeah. And that was a 1 hour talk, sorry.
Okay, those of you who have questions, alert us and we'll bring the mic to you, because we're needing to put a mic on you so that those online can hear you. You got a question way in the back. I'll go get it, Terry.
Hi there. I have a stupid question. So anyway, when you said you were in Gallup, New Mexico, and you were unsuccessful and there was all this mud and stuff, well, how would you, like there's all these rocks and stuff, how would you even know which one was a meteorite?
Right. So a question is, how do you know if it's a meteorite?
Yeah, or just some rocks or what?
I'm not really that qualified, other than I know one way is that they can be magnetic. So if they have iron in them, you can have a magnet, and that's one way to determine. There's a lot of false detections. You would bring it up the road to ASU, the Center for Meteorite Studies, which they probably don't want to be bothered with unless they're really legitimate. And then you can determine if it has a fusion crust on it when it entered. So it gets this crust over the top of it. And there are other ways to do that. So one of the stories, we had a pretty crazy amateur astronomer. Imagine that, crazy amateur astronomer in the Phoenix area. And he went to the desert of California looking for meteorites. And he didn't want to get out of his car. He wanted the air conditioner to keep going. And he knew he could drive back and forth. So he taped a magnet to the end of a 3-wood, a golf club, and then just went along like that. And then he found one. That was the best part, was he actually described it that way. So it's one way of doing it.
I had heard that if you would put a magnet in your backyard, perhaps pointed to the sky, and left it there for a long period of time, you would collect little flakes of meteorite material. Is that right or not?
Does anybody know the answer? I don't know the answer to that, and I'm not going to fake any answers or anything, but it sounds legitimate. Like there's always micrometeorites raining down on us, so you would think, yeah, you would. Oh, Dave Viker's the resident expert here. Yeah, yeah, that's always raining down, right? So, okay. Yeah, yeah. Okay. So it sounds legitimate. Yeah, yeah.
I think this might be two questions, but I don't know what fuels these asteroids to keep going. I mean, do they run out of gas like in a car? That would be the first question. I mean, they could keep going and then they just stop. The second question is, can you reel them in like you reel in fish, say, so that we could use the minerals, like we need rare earth minerals, but rather than taking them out of the ocean, can we get them from the asteroids?
I'm having the hardest time understanding. I'm sorry, my hearing's bad, so oh. Yeah, again, I can't answer that. I'm sorry. It sounds cool though. So I'm like batting 1 for 3 on answers here, so. Somebody asked me an easy question. What's the center of the solar system?
Sorry if that was too esoteric.
How are you? Thank you for the presentation. I had a very basic question.
Speak loud, please.
Okay. Thank you for the presentation. I have a very basic question about one of the laws, like trajectories of the asteroid. So throughout its rotation, it was just changing its brightness and luminosity. Why do you think it was because of this change? Like what caused this change?
What causes the change between the brightness of the asteroid? Oh, when it's rotating, the main thing here, without spilling. So here's your asteroid and it's rotating, and how bright is it now? And how bright is it now? So it's going to be like a fourth as bright here as when it's like that. And all of the, not all, most of the asteroids have some irregular slightly elliptical shape, sometimes extremely elliptical. So the easiest explanation is that it's a football shaped thing, and sometimes the short part's presented to you. That's the obvious way to see rotation. Another way would be it could be spherical and have some change in the terrain topography, like a crater with the rim or a mountain that'll brighten periodically every time it rotates. And so you combine both of those, and that's how you get these shape models. And thank you for putting a simulated asteroid up here.
Yes, I just completed the meteor observing program with the Astronomical League.
Oh.
And one of the requirements is we send our data to a place over in Chula Vista, California. Do they collect it and then send it to a central, I guess, warehouse or wherever they collect all this stuff? Or are there different organizations?
I know there is, I don't know how active it is today. There's the International Meteor Organization, was always the clearinghouse for this kind of data. So when you're observing, when you do this program, which I was totally unaware of, do you tell them like where it was in the sky and estimate its angle?
Yeah, what day it was, what time, down to the minute, down to the second.
Oh, good.
How long
Yeah.
was the trail,
Yeah.
how bright was it, and all these other different.
So one of the places that, and I can't name the site, the website offhand, when there's any kind of bright meteors, it's surprising how many people describe it. Then you'll get a map, say of Arizona, that will show all the vectors, right? It'll show what somebody in Tucson saw and then what somebody in Flagstaff saw, and they're entirely different vectors. And from that, you can begin to triangulate on where did this thing come from and where might it have landed. So if they're bright enough, it would go into that data as well. And I've never looked into where that comes from, but when there's a really bright meteor, I'll go to that site. And then also on that site, it'll give you what's the experience of the observer. Like, did they say, oh, it was over that way, but I don't know which way north is, then that's a 1. And then a good observer is somebody like an amateur astronomer like yourself who can actually describe things.
Yeah, because you're supposed to tell them where you are,
Yeah.
and then I usually included a description of the what the sky looked like or what constellation it was in.
Yeah.
And that time it went by this star and then it headed toward this star. So
Yeah.
it started to get a path across the sky. And I'm assuming somebody else saw it from a different angle and maybe they be able to triangulate where it landed or something.
If I was doing that, that would have been my first question before I started. Okay, how's this going to get used? Yeah,
Yeah.
career engineer. I don't want it. I'm sorry. how should I?
Yeah,
be-
yeah. It's an organization in Chula Vista. Yeah, it's related. They do a lot of other stuff there too, but I had to send it to them.
Yeah.
Less than 1 month old. It can't be any more than a month old.
Yeah.
Any observations?
Yeah.
So.
I could think of worse things to do than watch meteors.
I just looked up on AI. Yes, leaving a strong magnet
Oh.
in your backyard, particularly in the gutters or under the downspouts, can collect tiny metallic micrometeorites.
Okay. Somebody has to, I'm doing it again. I'll go to Jennifer. Sorry, did you hear I just can't hear questions that are that faint. Oh, man, why did you? All right. Oh, there we go. Yes, leaving it here. I'll answer the question here. So that is your answer to whether you can collect micrometeorites with the magnet, and you can. So that's really what you wanted to know. Yeah.
Any other questions in the back?
Yeah. Wait till he gets down the stairs and then.
Okay. Doesn't look like there's any others in the room. How about on social media?
I'll add that when I was a kid, I collected all the rain water off the roof the first time we had a monsoon storm, and I caught something tiny. I'm telling myself it was a meteorite. Teeny tiny little thing. I could see it under a microscope. So on YouTube, there's one comment. Hi from Australia. Love asteroid occultations. And then his question is, how do we get detailed imagery of asteroids with radio telescopes?
Probably what I showed in the slide is about the extent of my knowledge. So all you're doing with that is you're not only able to receive signals with the radio telescope, but you can send them. You know, that's how we get Netflix and all. So, so you're actually, if the asteroid is close enough, you can send a signal to that asteroid, and you send multiple signals to that asteroid, and as it rotates and moves, you can characterize its shape by how long did that signal take to come back to you versus how long it took to get there. And you can also look at the Doppler shift, like how much red shift or blue shift of that radio transmission. And that's done by, I've seen an entire talk on this by Lance Benner from JPL, who's the expert at that. And that's what he starts with, is with that, and then moves on through the work that they're doing. And as long as they continue to be funded, maybe, then we'll have asteroids being radar imaged, but kind of fat chance these days. Good.
We just have one comment on Zoom. It was from Matthew Oda. Just says, now the Vera Rubin telescope has discovered thousands of new asteroids that can be named eventually. So there's going to be a lot more asteroids coming with the Vera Rubin.
Yeah, it's going to be a lot more than thousands, because it can reach down to 24th magnitude and have a field of view that's many full moons wide, and then do it multiple times. And it's going to be, in my opinion, greater than anything Hubble Space Telescope. I know and James Webb Space Telescope. And since I'm spouting my opinions on astronomy, I think it will be the greatest thing we've done since maybe the Palomar Sky Survey, which, you know, is still getting used today to make discoveries, and still second place to something that's not American, which is the Gaia mission, which has just unbelievable amount of information. 1% of all the stars in the galaxy are characterized with their parallax and proper motion, usually with errors that are less than 1%. And that's just invaluable for so many areas of astronomy and will be for decades to come. And I love stuff like that. That's not done with 8 meters of aperture. That's done with 2 very humble sized telescopes in orbit. And that's, yeah, that and yeah, and Vera Rubin is just great. And I hope everybody here got to see the mirror at the Ceres Mirror Lab. That was really exotic to see something with the multiple curves that our buddy, the late Dean Kettleson, was involved in. Right.
Another question on
Oh,
Zoom
yeah.
from Matthew was, will the capability of the Vera Rubin telescope eclipse any more efforts to discover asteroids the old-fashioned way?
Oh, to discover asteroids like for amateurs? Oh, that's already close to done. So yeah, already when I talk about these 1.5 million asteroids, the last few 100,000 that were discovered were 23rd magnitude kind of thing. And so unless you have a dedicated program with at least a 1 meter telescope at a dark site, I'm sure not going to do it from Tempe with any aperture. So that's almost all being done by professional surveys already. And so, yeah, it will completely eliminate that part of the game, but there's always follow-up work to do on those asteroids. And that's what we can still do. I'd mentioned that so many Tucson references. So Roy Tucker was in one of the slides, and I'm going to forget the number, but it was hundreds of asteroids that he discovered. There was a short window where main belt asteroids that were 18th magnitude, which is pretty bright, hadn't been discovered yet. And people who were enterprising in the late 90s, amateurs, were discovering these asteroids. And Roy Tucker and then Paul Comba up in Prescott discovered 2 of them, added another 1,500 discoveries. And then quickly, the asteroids you could discover were 19th, 20th, and now they're out of reach. Yeah.
Okay, Tom, thank you so much.
What? Yeah.
It's pretty cool when they name celestial objects after you. Pretty nice, isn't it? And Tom, one of the things about his work is that it shows you that amateurs still have a role in doing real science. Now, with respect to discovering new asteroids, maybe that time has passed. But there is still plenty of science out there. And I know there are a number of our members who do real science. And since Tom dropped the name Gaia, it just inspired me to make sure that you take a look at this month's bulletin, because real science was being done this month. Oh, I'm sorry, in April, last month, at the B.G. Stinger Observatory. That class from the Gila County Community College was there doing observations of Gaia objects. Now, Gaia did a wonderful survey of our galaxy's stars. It has characterized almost 2 billion stars with respect to lots of parameters in terms of their color and position and motion and so on. But it did have trouble with some 100,000 stars. And the reason that it may have had trouble with those 1,000 stars is they weren't just stars, they were binary stars. And this effort through Gila Community College, we had the 4th group that was doing observations of some of those 100,000 stars. And 3 Gila Community College groups already have finished their evaluations, and together they have discovered 45 new binary stars. Never known before, 45, 100,000 to go. And at CAC this past month, Bob, how many were discovered? 6? 5 or 6. We're still doing the data, and I don't want to. They're working on a paper, so you'll see it in print here, perhaps in the next couple of months. But real science still can be done by amateurs. We hope to turn this into a program where we can have many members participating. There were 7 members of the team that were required to do these observations, from telescope operator to logger to, we had somebody that had to turn a dial to flip a mirror from one camera to the other. So there's all kinds of jobs that anybody can do, and we're going to try and get as many members to do that kind of science here in the future. So stay tuned. Some amateur science is still happening. Okay, talking about the solar system, Eric Kakashka gives our monthly report on planets in the sky. You can also find his report on the website. And Eric, what's happening?
When you look to the west in the evening, you see bright Venus. It's quite far north now and reasonably high up. So it's actually close to the middle of the apparition from February to October. So by the end of the month or so, it's about as well visible as it gets for this evening apparition. And then after the 22nd of May, Mercury joins Venus, but it's 20 degrees below and it's not as well visible, but it's still easy by the end of the month at least. On the 22nd, it's still difficult to see. And then if you go high up in the west, there's then the next brightest object after Venus. That's Jupiter. Right now, when it gets visible, like this evening, it's still 50 degrees high, so it's really good for observing in a telescope or anything else. But then by the end of the month, it will be only 25 degrees high, so you can see that after the end of the month, there isn't that much time to observe Jupiter in the evening sky. And it sets already before midnight, so that's why it gets, the visibility gets short. And then once Jupiter's done, then there's no planet in the sky for a few hours. And then in the morning sky, Saturn rises around 4 a.m. now, but later in the month it will get to 3 a.m. So it will be reasonably well visible because there's just no other bright star in the area in the east or southeast in the morning sky. So it's the brightest object around there. It's the constellation Ceres. And finally, Mars, the other bright planet that I haven't mentioned yet, that is really just barely visible in the morning sky. You have to know exactly where to look, just right in the east, just at the right time. But over the next half a year or even longer, it will become better and better, and then eventually will come to opposition on late next winter. The moon is full. It was full today, and it's just probably rising. Yeah, just rose 10 minutes ago or so. So you'll see it once you get out of the room in the southeast or so. And in 2 evenings, it will be close to Antares, and then 27 days later, on the 30th, it will be close to Antares again. And in between, about halfway in between, on the 14th, it will be above Mars. And so on the 14th, when you look at the crescent of the moon, and then you can find Mars. On other days, it's pretty difficult. And then 4 days later, it will be back in the evening sky. It will be only 2 degrees from Venus. And with Venus and the crescent moon really well visible in the evening sky, that's probably just the best view we have this month. And if you have a telescope, then it's still nice to watch the Galilean satellites. because Jupiter is so well up in the early evening. And so on the 15th, after 10 p.m., we have the shadow of Ganymede going across the disk. And also on the 22nd after 10 p.m., but this time it's not the shadow of Ganymede, but it's actually the moon itself. So the moon itself is also darker than Jupiter, but not as dark as the black shadow. And that's for this month, so happy observing.
Thank you, Eric. Always good to know what's happening. And we've got a moon tonight, so I think we're going to have 2 moons this month, right? And it's okay, we got a lot of amateurs here that know it's a blue moon. Yes, good. Okay. I think this is probably a good time for us to bid adieu to our visitors on social media, and we're going to move into some club business. So thank you for joining us, and we will see those folks next month. The next meeting will be the first Friday of June, and that'll be just ahead of our Grand Canyon Star Party. So I hope we have a lot of members here, but I know that there's some members are going to be at the Grand Canyon already because it starts the following day. But we will